So, in the last class we obtained an integration method which is a Newton-Cotes method for equally spaced points, namely the Simpson's rule, in which the curve y is equal to f of x in an interval x0 to x2 is approximated by a quadratic interpolating polynomial p2 of x, and this resulted in Simpson's rule such that integral a to b f of x dx is given by h by 3 the sum of the end ordinates plus 4 times the intermediate ordinate plus the error term, where the error term is given by this, showing that E is of the error E is of order of h to the power of 5 in Simpson's rule. Here h is x2 minus x0 divided by 2. So, we divide the interval into 2 equal parts and get the Simpson's rule. So, we would like to see how the accuracy can be increased. So, in which case the error must be reduced. So, that suggests that we must make the step size h smaller and smaller, which is equivalent to dividing the interval x0 to x2 into a number of equal subintervals. But we observe that in Simpson's rule we have to divide the given interval into even number of equal subintervals, because we want to approximate a curve in an interval of the form x0 to x2 by means of a quadratic interpolating polynomial p2 of x passing through 3 points. And so, we have to divide the interval x0 to the end point or a to b into an even number of equal subintervals and apply Simpson's rule in each of the appropriate intervals and see what we get. This results in an integration method which is called Composite Simpson's rule, where my integration is between a and b. So, I divide a b into even number of equal subintervals. So, divide a b into even number of equal subintervals by means of points, say x0, x1, x2, etc., x2n, so that x2n minus x0 divided by, so when we divide it into 2n equal subintervals, so we get the step size h to be such that x2n minus x0 divided by 2n will be equal to h. And now we take the subinterval between x0 to x2. So, we have 3 points x0 f of x0, x1 f of x1, x2 f of x2. So, passing through these 3 points, I can get an interpolating polynomial p2 of x, and the curve y is equal to f of x in this interval is approximated by a quadratic polynomial passing through these 3 points x0 f0, x1 f1, x2 f2. Similarly, in the interval x2 to x4, again I approximate the function by a quadratic polynomial that interpolates this function at the points x2 f2, x3 f3, x4 f4, and I continue this, and I will have the last interval to consist of the points x2n minus 2, x2 2n minus 1 and xn. So that in this interval x2n minus 2 to x2n, the function is again approximated by a quadratic interpolating polynomial that interpolates this function at the points x2n minus 2 f2n minus 2, x2n minus 1 f2n minus 1 and x2n comma f2n. So, thus that suggests that integral a to b f of x dx, which is integral x naught to x2n f of x dx, is going to be integral x naught to x2 f of x dx plus integral x2 to x4 f of x dx plus etc. plus integral x2n minus 2 to x2n f of x dx. So, now in each of these intervals I can apply Simpson's rule. I know how to get the ordinates appropriately and then apply this rule on the right hand side, which is given by Simpson's rule. So, I will have h by 3 into, in this interval, f naught plus 4 f1 plus f2. In the next interval, h by 3 into f2, that is the value of the ordinate at x2, plus 4 times the intermediate point, that is x3 plus f4. What do you think in the next interval it will be? H by 4 f4 plus 4 f5 plus f6, and continue this, and in the last interval it is going to be h by 3 into f2n minus 2 plus 4 into f2n minus 1 plus f2n. So, we simplify and see that it is h by 3. I observe that f naught and f2n appear once. So, I just write down this group of terms which corresponds to sum of the end ordinates. Then I observe that I have terms 4 times f1 plus f3 plus f5 plus etc. plus f2n minus 1. I have terms which corresponds to sum of the odd suffixed ordinates. Then I look at the even suffixed ordinates. I observe that each of these even suffixed ordinates appears twice. So, I have twice f2 plus f4 plus etc. plus f2n minus 2. So, I can say that composite Simpson's rule gives you a method for evaluating integral a to b f of x dx approximately, and it is given by h by 3 into sum of the end ordinates, 4 times the odd suffixed ordinates plus 2 times the even suffixed ordinates. So, it is now important to see what is the error in composite Simpson's rule. That can be easily obtained because we have applied Simpson's rule in each of these intervals, and we already have computed the error term in Simpson's rule. So, I apply the error in each of the intervals, and so I get the total error in composite Simpson's rule is going to be the error that occurs due to integration in this interval, and that will be minus h power 5 by 90 into the fourth derivative at say some psi naught. Then the error that arises due to this integration. So, minus h power 5 by 90 into fourth derivative say at psi 1 and so on, and then from the last integral we will have the fourth derivative appearing at some psi which is 2n psi 2n minus 2. So, I have added the errors that occur due to application of Simpson's rule in each of these integrals. So, that gives you minus h power 5 by 90 into the fourth derivative at psi naught plus fourth derivative at psi 1 and so on, the fourth derivative of f at psi 2n minus 2. So, since the requirement for the function f in order that this formula is valid is that the fourth derivative exists and is continuous in that interval. There exists a psi in this interval x naught to x 2n such that how many intervals in which you have applied Simpson's rule? You have applied Simpson's rule in each of the n, capital N subintervals, because you have divided the entire interval into 2n equal subintervals. You apply the Simpson's rule in n, capital N subintervals. So, there exists a psi in this interval such that capital N times the fourth derivative at psi will be equal to the fourth derivative at psi naught plus fourth derivative at psi 1 plus etc. plus the fourth derivative at psi 2n minus 2. So, I can use this and then get therefore the error to be equal to minus h power 5 by 90 into n times the fourth derivative at psi. But I know that x 2n minus x naught by 2n is h. So, that will give me x 2n is b, x naught is a divided by 2h to be equal to capital N. So, we substitute that here. So, minus h power 5 by 90 into n is b minus a by 2h into fourth derivative at psi, where psi is in the interval a to b. So, this gives you minus h power 4 by 180 into b minus a into fourth derivative at psi. So, you observe that the error in composite Simpson's rule is of order of h to the power of 4. And the error term clearly shows that composite Simpson's rule is exact for polynomials of degree up to 3. So, up to cubic polynomials, the method is exact. The error will be 0 if f of x is a polynomial of degree less than or equal to 3. That is what the error term tells. So, composite Simpson's rule is exact for polynomials of degree less than or equal to 3. So far we have used the polynomial interpolation in deriving numerical integration methods, where the polynomial interpolation is done with equally spaced points. So, we shall now explain another method which is called method of undetermined coefficients, using which one can derive integration methods where the points, namely the nodes xi, need not be equally spaced. So, let us explain what is the method of undetermined coefficients. So, using this method, one can obtain integration formulas for evaluating integral a to b f of x dx by requiring that this integral is of the form, say, sigma k is equal to 0 to n c k into f of x k. And the constants c k can be determined in such a way that the method is exact. Method is exact for polynomials of degree. So, let us see up to what. How many unknowns are there? Ck's are n plus 1 in number. K runs from 0 to n. So, there are n plus 1 unknowns which have to be determined. The xk's need not be equally spaced, but the location of the points will be specified to you in the interval a to b. So, derive an integration method by seeking the constants ck in such a way that this method is exact for polynomials of degree. So, you require n plus 1 conditions. So, for polynomials of degree less than or equal to n. So, you will have n plus 1 conditions coming from here. When you use those conditions, you will be able to determine the constants ck. So, since you determine the coefficients in the integration method which are unknown by requiring that the method is exact for polynomials of degree less than or equal to n, the method derives its name that it is a method of undetermined coefficients. So, we shall illustrate this by means of the following example. So, let us obtain constants a, b and c such that integral 0 to h f of x dx is h into a times f at 0 plus b into f at h by 3 plus c into f at h. So, derive integration method of the form 0 to h f of x dx is equal to this, where a, b, c are constants such that this integral method is exact for polynomials of degree as high as possible. As high as possible. And you observe that this interval of integration is from 0 to h. The ordinates that appear here are f at 0 and f at h by 3, and the third ordinate is f at h. So, the points say x0, x1, x2, they are not equally spaced. They are located in that interval, namely 0 to h. So, this illustrates how method of undetermined coefficients can be used to derive integration methods where the nodes need not be equally spaced. Of course, the method can be applied to the case where the nodes are equally spaced also, but in case the points are not equally spaced, then the method works well. So, let us obtain the constants. What does it say? We want this method to be exact for polynomials of degree as high as possible. And we observe that the method involves 3 arbitrary constants. So, we require 3 conditions. So, we require 3 conditions So, we make the method exact for polynomials of degree 0, 1 and 2. That would say that when f of x is a constant, when f of x is x and f of x is equal to x square, the method must be exact. So, find a, b, c such that the method is exact for polynomials of degree less than or equal to 2. So, let us substitute integral 0 to h, f is 1, that will give you h into a f of 0 plus b f of h by 3 plus c, and that gives you integral 0 to h dx is x between 0 and h. So, that is h. So, that gives you the first equation a plus b plus c equal to 1. Then let us take f of x to be x. So, 0 to h, x dx must be equal to h into a times f of 0, f of x is x. So, f of 0 is 0 plus b into f of h by 3, f of x is x. So, f of h by 3 is h by 3 plus c times f at h, and so it is going to be h. And what is this? It is integral x dx. So, x square by 2 between 0 and h. So, it is h square by 2. So, which gives you the condition, I can cancel a factor h. So, this gives you b into h by 3 plus c into h is equal to h by 2. So, b by 3 plus c must be equal to half, that is the second condition. And thirdly, we require that 0 to h x square dx must be equal to h into a f of 0 plus b f of h by 3. So, h by 3 the whole square plus c into f of h. This must be equal to integral x square dx. So, x cubed by 3 between 0 and h. So, it is h cubed by 3. So, that gives you h into b h square by 9 plus c h square is h cubed by 3. So, cancelling h cubed on both sides, we get b by 9 plus c is 1 by 3. So, we have 3 equations to determine the 3 unknowns a, b and c. So, we have b by 3 plus c is half. So, multiplying by 1 by 3, I get b by 9 plus c by 3 is 1 by 6. So, subtracting this from here, I get c minus c by 3 is 1 by 3 minus 1 by 6. So, which is 1 by 6. So, 2 by 3 c is 1 by 6. So, c is 1 by 4, and therefore, b by 9 must be 1 by 3 minus c. So, that gives you 1 by 12, and so b is 9 by 12 or 3 by 4. But I know a plus b plus c must be 1. So, a must be 1 minus b minus c, and so a must be 0. So, we have evaluated the constants a, b, c. So, we can write down the integration method. So, 0 to h f of x dx is h into a is 0, b turned out to be 3 by 4 into f at h by 3 plus c is 1 by 4 into f at h. So, it is h by 4 into thrice f of h by 3 plus f at h. So, this integral is approximately the value on the right hand side. So, what does this involve? If you want to integrate between 0 and h, then this says it is h by 4. What is that h? The h appears as the upper limit, right? It is not the step size, it is what appears as the upper limit. So, 0 to h. So, that gives you h by 4 into thrice f of h by 3 plus f of h. In fact, since the interval of integration is 0 to h, the length of the interval is h. So, the ordinates are taken at the total length of the interval by 3, that is one of the points, which is our x1, and the other one is at this end point. So, evaluate these two ordinates and then apply this rule, you will get the value of the integral approximately. So, we compute the error and we see that it is 0 to h f of x dx minus h by 4 into thrice f of h by 3 plus f of h. That is one way of computing the error. Namely, we will say that we make use of the fundamental theorem of integral calculus and say there is a capital F of x such that f dashed of x is equal to small f of x, and then substitute f dashed of x, evaluate the integral and then use Taylor's theorem and compute what is the first neglected term or what is the leading order error term. The other way of evaluating is to see, is this method exact for polynomials of degree 3, namely when f of x is equal to x cubed, is the method exact? Let us try. So, by taking f of x is equal to x cubed, in that case 0 to h, f of x is x cubed dx, and the method gives you minus h by 4 into thrice f of h by 3. So, h by 3 the whole cubed plus f of h, which is h cubed. So, this gives you x power 4 by 4 between 0 and h. So, it is h power 4 minus I have a h power 4 by 4 into 3 by 27, 1 by 3 cubed plus 1. So, that gives you h power 4 by 4 minus h power 4 by 4 into 30 by 27, which gives you h power 4 by 4 into, let us simplify, or we can keep h power 4 by 4 as it is. So, 1 minus 10 by 9, which gives you minus h power 4 by 36. So, the difference when evaluated by taking f of x to be equal to x cubed is not 0, and it is equal to minus h power 4 by 36, and we have taken a polynomial of degree 3 here. So, we can now write down therefore the error in this method which we have computed. So, the error in this method will be, the method is exact up to polynomial of degree 2 the error contributes to a non-zero value when f of x is taken to be x cubed, and it is exact for polynomials of degree less than or equal to 2. So, we can write down the error immediately as minus h power 4 by 36 into the third derivative evaluated at psi, where psi lies between 0 and h. So, this tells us that the function f or the class of functions f for which this integration method can be applied, and it also tells us that the method is exact for polynomials of degree less than or equal to 2, so that the error will be 0. So, using method of undetermined coefficients, we have been able to derive an integration method where the nodes need not be equally spaced. So, now you can try to see what happens if you want a method of the form, say integral a to b f of x dx, such that it is capital A times f at a plus b f at a plus b by 2 plus c into f at b. So, determine a, b and c such that the method is exact for polynomials of degree as high as possible. So, here you observe that the points are a, b and a plus b by 2, which means this is the midpoint of the interval. So, the points are equally spaced. I would like to derive this integration method using method of undetermined coefficients and find a, b and c such that the method is exact for polynomials of degree as high as possible. And you would immediately see that you are essentially deriving Simpson's rule for equally spaced points, but now using the method of undetermined coefficients. Earlier you derived Simpson's rule using polynomial interpolation with equally spaced points, but now that we have learnt the method of undetermined coefficients, I want you to derive Simpson's rule for equally spaced points, namely a method of this form which would give you Simpson's rule, so that the constants a, b and c, what do you expect a, b, c to be? A will come out to be h by 3 and b will come out to be 4h by 3 and c will be again h by 3. So, derive a method and also compute the error using, say, once you get the method, you know that the method is exact for what polynomials? You require 3 constants. So, polynomials of degree 0, 1 and 2. You will use these 3 conditions to derive a, b and c. Then check what happens when f of x is equal to x cubed. You already know result about the error in Simpson's rule. Check what happens and then work out the details, because you want the method to be exact for polynomials of degree as high as possible. So, that completes our discussion on method of undetermined coefficients. We move on to another method which is called Gaussian quadrature, that we will take up in the next lecture.